Today I want to go on to deduce the so-called wave equation. So in the preceding lecture we saw that the decay of the voltage is proportional to the serial voltage drop on the series elements, and we saw that the decay of the current is proportional or equal to the current which flows through the parallel elements. So to deduce the so-called wave equation, we will do a second derivation of this, of the voltage. So we will get, this is the second derivation of u of z with respect to z square. Of course, these elements are independent of the z coordinate because the transmission line is homogeneous, so the derivation will only apply to the current. So we will have this is R plus J omega L prime times the derivation of the current with respect to Z. And of course you see here this derivation with, of the current, or the decay of the current, is equal to this. So we must account for the negative sign here. So this will be then equal to minus R prime plus J omega L prime times G prime plus J omega C prime times U of Z. And of course now we can bring this onto the other side, so we can change the side and we get the second derivation of the voltage function with respect to z square minus R plus J omega L times G prime plus J omega C prime times U of Z is 0. This is a differential equation, of course. We see this as a second order differential equation, and it's homogeneous and the coefficients are constant. And the next step, we will use a so-called drive function to solve this equation. Up to now we found that the voltage function must fulfill this differential equation, and to solve this differential equation it's the easiest way to talk with a mathematician, and a mathematician would suggest that we try to use the exponential function. So we can formulate, let's assume that our function u of z is somehow a constant u naught times the exponential function of minus gamma times z. Of course, at the moment we don't know if this function is able to solve this equation, but of course we can now do a derivation of this function with respect to z, u of z with respect to z. Of course, then this is a constant, and you see here this exponential function will reproduce gamma, so we will get minus gamma times u naught times exponential function of minus gamma times z. Or you see here our original function appears, so we can say this is minus gamma times u of z. This, as a result, you see if you derive the function u of z, then this derivation with respect to z goes over into a multiplication with minus gamma. So if I do the second derivation, z square, Then of course you see this is minus gamma. Of course we assume gamma is a constant. And we again have to derive the function u of z with respect to z. And we already know that this goes over into a multiplication with minus gamma, so as a result we will get gamma squared times u of z. As a result, we can now substitute the second derivation of the function by this term. So we can formulate now that gamma squared times u of z minus r prime plus j omega L prime times g prime plus j omega c prime times u of z is 0. And you see here in both cases we have u of z, so we can rewrite this in two terms: gamma square minus r prime plus j omega L prime times g prime plus j omega c prime times u of z has to be 0. You see here we have a function or an equation consisting of two terms. So to solve this equation we can assume that the voltage all over the transmission line is 0, but this would not be of interest. Normally the mathematician called this the trivial solution. The non-trivial solution exists if this term itself becomes 0. This is a so-called non-trivial solution, and we see now that gamma square must then be equal to r prime plus j omega L prime times g prime plus j omega c prime. And of course we can take the square root of it. Would be the square root of r prime plus j omega L prime times g prime plus j omega c prime. But if you, as soon as you take the square root, you have the possibility to choose whether a positive or a negative sign. As a result, we see that gamma can have two different values, and this again means that we have in principle two possible solutions, one with a positive sign, one with a negative sign, and one with a positive sign. So in the following section we will first discuss the gamma with a positive sign, and here of course then with a negative sign. What we found up to now is this differential equation, and we saw that this function is a solution if gamma is chosen according to this equation. And we know, for example, that the derivation of the function u of z with respect to the z coordinate is given as r prime plus j omega L prime times I of z. Of course, now we can solve this equation for the current, and we will see that I of z is given by minus 1 over r prime plus j omega L prime times the derivation u of z with respect to z. So now we can in principle solve for the current distribution on the transmission line. So of course we remember that the derivation with respect to z of this term results in a multiplication with minus gamma. So we can conclude that I of z is equal to, the minus sign will disappear, so it's equal to gamma divided by r prime plus j omega L prime times u of z. And we have here a term which is only dependent on the parameters which describe our transmission line, and normally we will introduce the so-called characteristic impedance of the transmission line as, we call it ZC. At the moment it will be a complex valued constant. So you see this will be just defined as r prime plus j omega L prime divided by gamma. And we know that gamma is given by the square root of r prime plus j omega L prime times g prime plus j omega c prime. And of course here we in principle could write it like this. This is the square root of gamma square, and then you see this term will cancel, and we can rewrite the equation for the characteristic impedance ZC to be the square root of r prime plus j omega L prime divided by g prime plus j omega c prime. So this is a further constant. We have to introduce two constants up to now. One constant is the constant gamma, which is composed from the parameters which describe the transmission line, and the further constant is now the so-called characteristic impedance. And if we have a transmission line which shows losses, then the characteristic impedance is normally a complex, or shows a complex value. I now want to summarize what we found. So we started with our equivalent circuit of the transmission line, and we found that if I'm looking for the function u of z, this function must fulfill this differential equation. And we found that the exponential function can solve this differential equation if we choose gamma according to this equation. So this is the first important parameter we have to discuss later. And we also found then the solution for the current distribution on the same transmission line. It's just the voltage distribution divided by its characteristic impedance. And as long as we have a transmission line with losses, we see that this characteristic impedance is also a complex valued parameter, which depends of course on the parameters of the transmission line. And those two parameters we have to define or discuss in more detail. We already termed this to be the complex valued characteristic impedance. Up to now we did not assign a name to this constant. So from a mathematical point of view we already found a solution, but now we have to discuss the physical significance or special cases for gamma and ZC and the characteristic impedance. So to become more familiar with our solution, we will now discuss our constant gamma. Of course, you see, according to this equation, gamma is a complex valued constant, or of course it's frequency dependent, but it depends on the parameters of the transmission line. And to make it easier to understand what will happen with, or what gamma does describe, we want to discuss first a lossless TL, a lossless transmission line. A lossless transmission line will be described if R, or is described if R prime is identical to 0 and also G prime is identical to 0. So both will vanish, and of course if you have a look then to this equation, we will find that gamma is then given by, of course this is 0, this is 0, and we have J times J will be minus omega square L prime C prime. And of course if we take the square root of the minus sign, this will result in J, and so we will find that gamma has to be chosen to be equal to J omega, the square root of L prime times C prime, and normally we will introduce this to be beta. So we say beta is equal to omega times L prime C prime. So to discuss now the influence of beta on our solution, we must remember our solution was given by U of Z is a complex valued constant gamma times the exponential function minus gamma, but gamma is now replaced by J beta. So we have here the exponential function of minus J beta times Z. So, and now in the first step I want to explain the mathematics here. What does it mean? So we can here first define a plane of the voltages. So I call this a U plane. So, and I will write here the real part of U and here J imaginary part of U. And we see at the moment we don't know how to choose this constant, so I just assume that this constant lies somewhere in this complex plane. So the green arrow will be U naught here. So this is a constant. At the moment we don't know if its value, but we see now what this term will do. You see here this is an exponential function which will change the phase of the voltage, and it will change the phase because of the negative sign in clockwise direction. So we can in principle use a compass and draw a certain circle. Of course here this circle will depend on, or the angle will depend on beta times z, and this term will then be, depending on the z coordinate, this term will be then u of z. So what we see here, beta will change the phase along the transmission line in clockwise direction, and that is why beta is the called phase propagation constant. Phase propagation constant, and the phase propagation constant is governed by the inductance per unit length and capacitance per unit length of our transmission line. In a further step, we also want to include in the discussion ZC here. Of course, up to now we discussed gamma, and for the special case of a lossless transmission line, a lossless transmission line is described by R prime, it's equal to 0, G prime is equal to 0, and then gamma becomes purely imaginary, where we have to choose beta to be equal to omega square root L prime C prime. And we saw in a mathematical sense, this exponential function will change the phase along the transmission line, and the phase change is due to this negative sign, will be in clockwise direction. When we remember the impedance, the characteristic impedance, we saw that the characteristic impedance is given by R prime plus J omega L prime divided by G prime plus J omega C prime. This is our characteristic impedance, and if we include the losses, but now of course these losses are 0, and of course then also this J will cancel and also the omega will cancel, and we find that this is given by L prime divided by C prime, or we can conclude that for a lossless transmission line, ZC shows a real value, L prime over C prime, and we, as a result, we can say lossless TL C, the characteristic impedance of a lossless transmission line, becomes a real value. And thus we can say that I of Z will be equal to 1 over ZC times U of Z. So we see that if I have chosen a complex valued function U of Z, according to this equation, we see that the current I of Z and the voltage U of Z are in phase. So there is no phase change between the voltage and the current, and of course in the next step, up to now we only did discuss the complex valued function, and the question is how do the function U of Z comma t, because with the help of the complex valued function we in principle described a sinusoidal function, and up to now we don't know how this function to behave. So we can say this is still to be done, and this we will do in the next lecture to discuss the behavior of this function.